Hello everyone, welcome to Dakshana e-classroom program. So in last lecture in surface tension we talked about axis pressure. We understood why there is axis pressure and what does it mean basically. So if we just look for a bubble or either drop, then we know because of surface tension the tendency of the free surface is to have always minimum surface area, and you can say each molecule on free surface is experiencing a net inward force. So that because of that the inner substance or fluid get compressed, and that result in higher pressure inside, and that is called axis pressure, or we measure that difference in inner pressure minus outside pressure, that is called axis pressure. We derived some relation for axis pressure for bubble drop and like cylindrical bubble, and even for a single curved surface on concave side there will be always axis pressure. Next, in today's lecture we are going to talk about capillary and capillarity action. This is a also important topic in surface tension chapter. So first let me tell you what is exactly capillary. What do we mean by capillary? Capillary here we mean basically is very thin narrow tube whose radius is very small. That narrow tube is simply termed as capillary. So you can say a tube of very small radius is a narrow tube, thin narrow tube called as capillary, right? So you can say a narrow tube or thin tube or a tube of very small radius is termed as capillary. Here the point next topic is capillarity action. So what does it mean basically? What is it? So let's consider here we have one container. Some liquid is filled in this container, and this small, like you can say this is the capillary of very small radius. Okay, this is capillary. So what if this capillary is submerged in this liquid? Then two things are observed depending on the pair of like properties of liquid and the capillary material. Is it solid? Either liquid in this capillary rises more than this reference or surrounding level, or it depresses, right? So means if we submerge, I mean like this capillary is placed like this, capillary is submerged or dipped in this liquid, then two situations are possible. Wait, so let's say this is the capillary, then either the liquid in this will rise like this above, this is the surrounding level, or it may just 1 second, it will be rising like this, or it may depress. So let me show you this part in sort of like zoomed condition. If you just focus on this, so let's say this is the level of liquid and this is the capillary. So here two situations happen: either the liquid will rise in this manner more than the surrounding level, or it will depress in this manner, right? So ultimately the level of liquid in the capillary, either it will ascend or descend compared to the surrounding level. This phenomena of rising or depressing of liquid in the capillary when it is submerged in the liquid container or liquid, this phenomena is termed as capillarity action. So the point here comes is that why this happened, why in a capillary liquid either rises, it does not happen simultaneously together. That's of course practically not possible. Like it's rising also and depressing, means depending on the pair of liquid and capillary, is it material, solid material properties, either it will rise like this or it will depress like this. Next, the thing, important thing about this phenomena is that we need to understand why this happen actually, and it has like many applications actually. You are able to write because of pen, is it? Some nail like ball pens are there. That is because of capillarity action. You see in plants actually, water level or minerals from rises from the bottom, is it, ground to the top height. That too is also because of capillarity action. Small, very small pores are there actually, and because of capillarity action the water and minerals keep on rising through those pores up to the top of the plant. So it has a lot of application also. We need to understand the physics behind it, that why this either rises or depresses, that we need to understand here. So capillarity action is simple terms we can say when a narrow tube, or we call that capillary, is submerged in the liquid, depending on either liquid in the capillary, liquid level in the capillary will ascend or descend compared to the surrounding level. This is termed as capillarity action. So here I can define, if a capillary tube is dipped in a liquid tank, then either liquid will ascend or descend in the capillary compared or with respect to surrounding level of liquid in the tank. This is called as capillarity action. So simple terms, like when a capillary is dipped in a tank containing some liquid, depending on the condition, depending on the property of, is it, so depends the ascending or descending of liquid level in capillary depends on the property of liquid and solid capillary. So whether it will rise or ascend or descend, that will depends on the properties of liquid filled in the tank, or the material, means properties of the solid material of capillary. And this phenomena we simply call as capillarity action. We can see many application of this in nature actually. Capillarity action. So ink rises in pen due to capillarity action. Similarly, water and minerals rises from ground to top of tree through small pores in the trunk of tree. This is also example of capillarity action. So now we need to understand the physics behind it, that why this actually happen and how physics explain this phenomenon. Okay, so let's understand this capillarity action or physics behind it, and next thing is like exactly let's calculate by what, like, or how much height the liquid will rise in the capillary. So let's calculate that ascent formula first. So here I am considering a container containing some liquid of surface tension T. Is it container containing liquid of surface tension T, and in this a capillary is dipped. Radius of small opening, radius of this capillary, let's say small r. This is the liquid rises. Small r is the radius of capillary tube, and height of capillary tube is sufficient. Let's say the liquid rises by height h. Height of liquid rises in capillary with respect to surrounding surrounding level, and theta is the angle of contact of liquid in capillary tube, and r is the radius of meniscus of free surface in tube. These are all like convention. Theta angle of contact, r radius of curvature of this free surface or meniscus, h is the height, small r is the radius of the tube, and t is the surface tension. So now why this rises actually, so we can understand that in two ways actually. Let's say method 1. Right, first let me zoom this part. So here we have, this is capillary. Let's say this is the surrounding level of liquid, and this is the level of liquid in the capillary. This height I am taking is h. So here what will happen actually, this will be angle of contact theta, that will be, this will be also equal to theta. This radius of the capillary, this is small r, and if this is the center, then I can write this is the radius of curvature, that is equal to capital R. So here this is theta, this will be also angle theta. I don't know, means I can draw the diagram a little bit bigger also. Let's say this is capillary, so this is further zoomed, then so this is then radius of curvature. Let's say this is the radius of curvature r, and here this will be angle theta, and I can write this will be small radius, and definitely this will be what, 90 degrees. This is theta, this is 90 minus theta, this will be also theta. So the relation between capital R and small r, I can write it from here, is it? So here what it mean, actually you can write capital R cos theta is equal to small r. That means capital R is equal to small r by cos theta, right? Capital R cos theta will be small r. Okay, so this is one thing we got. Now next thing is, let's understand why. So we can understand that in two ways. One is, actually what is this? This is the concave side. So concave side means at this point pressure will be what? Axis, right? Just pay attention here. You have noted down, remember these things, conventions. Now I am trying to explain you why this happened, and that too there are two ways we can understand this. So I am explaining first method. Alright, so let me consider, let's say this is capillary, I'm like container, capillary, and let's say the liquid is here, only up to here, and it's not rising, right? Let liquid in capillary does not rise. Now what will happen? Because on this side it will be concave, is it? Concave side, so the pressure will be higher, and at this point, let's say this is point 1, A, B, C. So at point like B and C, you can just consider they are almost at same level, just below. So what it means, if we are having 2 points at same level in same liquid, then pressure at point B must be equal to C. 2 points in same liquid at same level. So that's why pressure at point, but because I know pressure at point PA is equal to PC is equal to what? P naught, atmosphere pressure, and by that axis pressure concept I can write PB will be equal to what? P naught minus 2T by R, if R is the radius of curvature of this meniscus. So what it implies, according to this, PB should be also equal to what? P naught, but it's actually less. So that is, this is contradicting. By concave surface, pressure at point B will become this, but because B and C are at same level, so pressure at B and C should be equal to P naught, right? And this is the contradiction, right? So because 2 points are at same level, so this should be the condition, but this is the pressure, is it, at point B due to excess pressure on concave side. So this is the contradiction. So that means it's not possible that level of liquid in this capillary is still remaining same. Clear? So liquid level will rise in the capillary, right? So here what will happen, the pressure liquid will rise in a manner such that pressure at point B, this B and this is point C, so liquid will rise in capillary so that PC become equal to P naught. So what was the like to become pressure at point B equal to P naught? How much? Here what is the pressure? At this point the pressure I can write at this point pressure is equal to what? Let's say this is I have not marked point D, so let me write this is point D. So PD can be written as what? P naught minus 2T by R. So at this point I want B point, the pressure should be equal to what? This 2T by R, it should rise. This height, is it? This rise in height should be balancing this 2T by R pressure, is it? So liquid will rise such that the excess pressure due to rise in liquid means rho GH, if rho is the density, should be balancing this 2T by R. Clear? I hope. So such that this excess pressure due to rise in liquid rho GH should balance this 2T by R. Now by this, so I hope you understood this. Now I can erase this part. Then I got this relation. So we have ultimately rho GH is equal to 2T by R, and this implies H is equal to 2T by rho G into R. And by this relation I can substitute capital R in terms of small r. So substituting for small r by cos theta equal to capital R, this H comes out to be 2T cos theta divided by rho Rg. This is the formula for height. This is the height by which the liquid will rise in the capillary. Let me tell you simple thing. In this situation, the liquid rises in the capillary. The rises because if it is not rising, then pressure at this point and this point will violate, will contradict. Is it? That I explained just now, that let's say liquid level is here, is it? Just see it here. If liquid at this point is also in same level, then pressure at this point will be P naught minus 2T by R. But at this point, and pressure at point C is P naught. So this is 2 points at same level and different pressure. That's not possible in same liquid. So that's why to balance, to make the pressure here at point B should be equal to P naught, press this level rises. And how much it will rise? So this additional pressure is balancing this decrease in pressure due to concave surface. So this is what exactly it's rising. And simplifying it, we are getting this is the expression. So this is method 1. We can understand that because on concave side there is excess pressure, means on convex side there will be less pressure, and this less pressure must be balanced to keep that property of liquid still validate, that at same point at same liquid at same level in same liquid pressure must be equal. So finally, after rearranging and writing all the things, we are getting this is the expression of height by which the liquid has to rise in the capillary, and where remember that small r is the radius of capillary. Let me explain same thing, same relation, same formula with different way, different method. So another way we can understand same thing, this ascent formula, the height h, is here we will see that the surface tension force will be acting this way and this way, and the angle of contact theta is this is theta. So what you can see, actually if I resolve this surface tensile force, then this is T, this will be also angle theta cos theta, and here also it will be T cos theta. on upward side it will be t sine theta. So you can see actually the horizontal component of tension force, is it, that is t cos theta, will exactly cancel out for each point. But you can see there is net vertically upward force, is it? But there is net upward force due to surface tension. And what is that upward force? So I can add that F upward is equal to T sine theta multiplied by how much? This periphery circumference, that will be equal to 2 pi into r. This I made mistake. This component will be cos theta and this will be sine theta. So here t sine theta will cancel out and upward force t cos theta will still stay there. So this net upward force means it's trying to lift the liquid. So this force, whatever the weight of liquid, it will be able to lift, that much liquid will rise in the capillary, is it? So this force will lift the liquid in capillary, that result in rising of liquid in capillary. In rise in level of liquid in the capillary. So next thing is, we can just balance this. Upward force must be equal to weight. So 2 pi r into t cos theta must be equal to what? Weight of liquid rises, that can be written as rho density multiplied by pi r square into h multiplied by g. So just pi 1 r gets cancelled. Simplifying h, we are getting 2t cos theta divided by rho rg, and this is the same formula we are getting that we got in the earlier case. So you can see it just same thing, we can look at it from different point, different views, different angles. One way is this upward component of tension force T cos theta multiplied by 2 pi r is lifting some liquid, and so this is balanced equal to the weight of liquid lifted, and just balancing, writing it, we are getting this H. Another way is on concave side pressure will be axis, convex side pressure will be low. That will contradict if liquid is not rising in the capillary, that will contradict the property or basic property of fluid. So to maintain that, it rises, so that pressure at same level in same liquid at 2 point must be equal. But the thing is, here we still have a little bit error actually in this formula. So we have one more correction actually. The correction comes is this force, we are writing it this weight, but actually what happened here, this is a, alright, we normally take this height is up to here h actually. So but we are ignoring this part, is it? But if we are adding that part also, then we will get better result. So this same 2 pi r t cos theta, we can write this is pi r square into h into rho into g, plus we will take this part as spherical, is it? So here. So let's say this is H, and now in this case we will take this is a completely hemispherical. This is assumption we take actually, that this curvature or meniscus is exactly hemispherical. So now we need to consider here this total force is equal to this weight plus this weight. So this will be equal to how much? That I can write pi r square into h will be equal to what? R. So this is r cube is the total volume of this cylinder minus 1 by 2, that is 1 by 3 or 2 by 3 pi r cube. So we are getting ultimately this is 1 by 3 pi r cube into rho into g. So this weight must be added, so pi r cube rho g divided by 3, and now rearranging it and writing it, we are getting h is equal to 2t cos theta divided by rho rg minus this is r by 3. This is the corrected and modified formula for height ascent or height h. Another important thing here is that the same formula is valid even when its liquid is depressing or descending. The thing is that if liquid is depressing, in that case theta will be like what? Greater than 90 degree. Theta will be greater than 90 degree, then this h we will have like cos theta will be negative. So automatically h will be negative. That means it is giving you the depression also, right? So let me just write you that case. So the descent formula also we can write. So consider this is the capillary, this is the liquid in the surrounding level, and in that case when it is descending the surface, the meniscus will be in this way. So here angle of contact theta will be greater than 90 degree. So cos theta will be definitely less than 0, negative. And exactly if we want we can go exactly step by step, otherwise it's exactly same manner, same method. By either method you can go, actually we will get still same expression. So h comes out to be here also 2t cos theta divided by rho rg. Same method is valid here, but theta will be greater than 90 degree. This implies cos theta will be less than 0. That implies h is less than 0. So here negative h implies it will give the descent or depth of liquid level in capillary. So normally, like if nothing is just normal situation is given, you are supposed to apply this formula. When special conditions are mentioned to you, even is it about this, then consider the correction and all that, some relation will be like hint will be given to you in the problem, then only you need to apply this formula, and that will happen actually rarely. Most of the time we use frequently this formula, and this formula will give you the result even case for the case of ascending and descending for both case. So this is about basically capillarity action. You must be clear that why this capillarity action, like what is the physics behind it, why the level of liquid in the capillary either rises or descended. And one more thing actually here, when angle of contact theta will be smaller or acute, the level will rise in the capillary. If angle of contact theta is obtuse, then liquid will descend in the capillary. So let me write this result here. Note, if angle of contact means theta is acute, then liquid will ascend in the capillary. And similarly, if angle of contact theta is obtuse, means greater than 90°, then liquid will descend in the capillary. And you should remember this case also. When it is ascending, then surface meniscus shape will be like this, is it? Theta less than 90°. And when it is actually depressing, then meniscus will be in this shape. Theta greater than 90°. So remember this: concave upward, convex upward. So this is the case for 2, this is the case for 1. This is also important point about capillarity action. So you must be now clear about all the things, why height rises and how much exactly and all that. Okay, so we understood the capillarity action and we got the relation here. H is equal to 2t cos theta divided by rho rg, or this can be also written as, that is also equal to 2t divided by rho g into capital R, where capital R is the radius of meniscus. So h into r is equal to 2t divided by rho into g, and that will be like constant. Okay, now my point here is that if, let's suppose here we are having this container and this is the capillary and liquid rises here up to this height h. So no doubt it will be rising up to here and it will be staying like this. And if next case, if the length of capillary is insufficient, what will happen in that case? So in this situation, let's say it's rising up to height h. If my capillary is only of length, let's say this is, let's say L, where L is less than h, what will happen? Is it? So in this situation, will the liquid comes out like a fountain? Out like a fountain? Or it will, maybe this is tube and liquid will like, is it, flow out or trickle along the liquid along the vertical wall of capillary. Will this happen? If either of this condition is happening, in both of these cases, in both of right side cases, it will be like violation of conservation of energy. They will violate the conservation of energy law. So that's why none of this will happen. neither this nor this. So in this situation, what happened actually when capillary tube length is of insufficient, like this, liquid rises up to here, height h. If this tube length is only up to here, L, then in this situation we have here h into r, 2t by rho g, so everything here is constant, is it? H into r will be equal to L into some r prime equal to 2t by rho g. This remains constant. So h changes, r will also change. H changes to L and r will change to r prime. So here, if this radius of curvature of meniscus, radius of curvature of meniscus of free surface changes to adjust the product H r must remain equal to L times r prime. L decreases, is it? H greater than L, r prime will be greater than r. So radius of curvature of meniscus increases, and by that it will adjust the decrease in height h, and so no fountain, nothing will happen. This will be the condition. Simply your r prime will increase, or radius of curvature of meniscus will increase. So this is about the case when we are having a capillary tube of insufficient length. Sometimes this question is asked like maybe in logical terms, maybe in mathematical terms. So mathematical terms, if you are given with the information h and r, you can keep the constant. L will be r prime, so whatever the condition, if h, r and L is given, r prime can be calculated. Theoretical things, if like it is given that if tube length is insufficient, then what will happen? Definitely it will not like flow, liquid will not flow like a fountain, it will not trickle along the vertical wall of the capillary, it will be simply adjusted and staying there with the complete full length L, but increasing radius of curvature of meniscus. Next things come here is that, let's say if capillary is tilted, is it? So let's say this, here we have situation, this is initially the capillary is in this orientation, and this is the liquid is rising up to height h. Next case, the capillary is tilted. Just wait. Okay, then what will happen actually? You need to relate it with the first explanation, that liquid is rising to maintain, to keep the pressure here constant. So here what will happen actually, liquid will rises in a manner such that this h remains constant. So this L, and if it is inclining, let's say at an angle phi, so if capillary is tilted, then h height of liquid will remain constant, but length of liquid will increase in tilted capillary. so that h become L, it will be equal to what? L cos phi, and this implies L will be equal to h divided by cos of phi. So this is the another possibility, another case. If capillary is tilted, in that condition simply your length of the liquid column will change in the capillary, but h will remain constant. That you can even relate to, because h is rising to maintain the pressure constant, and for because decrease in pressure is same, so that's why the height must remain constant, so that the pressure is balanced here. At same level the pressure must be constant. So this is all about your capillarity action. Okay, so next case of capillarity action is like this, is just a little bit different here. What is happening? There is one reservoir, water reservoir, or maybe some other reservoir, and two like parallel plates are dipped in this. So if you look at it from the front view, front side, this side, then it will appear like these are, this is the reservoir, and the capillary, and like these plates will appear like this. So the liquid will rise in this manner actually, is it? Now depending on if the angle of contact here is theta, is it? If I write angle of contact theta, then what will happen? T will be here, let's say its length is L, okay, and the separation between them, let me take it simply A. Then I can write here in this situation, net upward force will be equal to what? T cos theta multiplied by L into 2, because on this side, on this side, and on this side, this should be equal to what? The weight of this should balance the weight, that is rho density multiplied by A multiplied by L, density into this is what, volume into height, basically h into G, right? So from here we are getting actually this L gets cancelled, h comes out to be 2t cos theta divided by rho A G. So this is the expression of height of the liquid, which rises in this case h when two plates are dipped in a reservoir. If angle of contact here, contact theta equal to 0, then your h will be simply 2t divided by rho A into G. Similarly here we can like discuss about another case when two tubes, is it? So two tubes of radius are concentric tubes, basically of radius R1 and R2 are dipped in reservoir. Then what will happen actually here? So we look at it from top, and this is one tube and another tube is like this, and they are dipped in reservoir like this. So the liquid will rise in this part actually, is it? So this will be the rise of the liquid. So here also we can see again exactly, if angle of contact is, let's say, theta, angle of contact, this radius, let's say R1, and the outer radius I will say R2, then here also we can write net upward force will be equal to the weight of this liquid. So in this situation we can write upward force is T into 2 pi R1 plus T into 2 pi R2, and this should be equal to the weight of liquid rising. So weight of liquid rising is pi R2 square minus pi R1 square into rho into G into H. So this implies just cancelling the pi, and this is T into 2 pi, this is R1 plus R2, and this can be written as pi R1 plus R2 into R1 minus R2 into rho GH. So this pi this cancels, so h here coming out to be 2t divided by, and one more thing, if we are taking the angle theta, then this will be like multiplied by cos theta, so it will be like cos theta, so here also it will be cos theta divided by, here we have rho g into r1 plus r2. So this will be the height of liquid column, or basically this is also acting just like a capillary, and here also if theta equal to 0, then cos theta equal to 1, then your h will be equal to 2t cos theta divided by rho g into r 2t r1 plus r2. So this is the expression, or in different case, one case when two plates are submerged or dipped in liquid or in some reservoir, here two concentric tubes of radius r1 r2 are submerged, then that is the expression. Method is remaining same, the upward lifting force you can just balance equal to the weight, and that way we can calculate the height of liquid rising in both the cases, and even in any other case if it is asked to you. There is one mistake actually I did here, r1 plus r2, so this r1 plus r2 part will cancel, not this r1 minus r2, so we will have actually this cancelled, and here it will be r1 minus r2, and this will be your r1 minus r2. This will be the final result in this case. Okay, so just take care of that. Okay, so consider here a capillary. So we are having a capillary of radius small r, this is small r, and capillary tube is in vertical position and filled with liquid such that the upper meniscus is concave upward with radius of curvature r1. Now if this height of the liquid column is given as h, in different cases you are asked to find what will be the shape of this lower meniscus. It will be concave upward, horizontal plane, or concave downward. So that will depend actually on h and different positions, different conditions. So let me comment, and in which case, in which condition it will be equal to like which orientation or shape will be equal to this or that, is it? So here pressure will be, I can write outside P naught pressure. Here pressure will be equal to what? P naught minus 2T divided by R1. Then pressure at this point, I mean like just above the lower meniscus, will be equal to what? This will be P naught minus 2T divided by R1 plus rho GH, if rho is the density of liquid. And definitely on lower side it will be pressure P naught, is it? And we know pressure, if it is equal, then it will be like plane, and whichever the side pressure is higher, it will be like concave that side, is it? So in this situation I can write, I got the pressure, let me write, this is pressure P1 here now, and pressure at the bottom side of lower meniscus, I will write this is equal to P2, is it? So here different possibilities, if P1 that is equal to P naught minus 2T by R1 plus rho GH, is it, is greater than P2, right? What it implies, and that is equal to P2 equal to, this means you can write P1 is greater than P2, that means it is like pressure is higher on upper side, is it? So this situation, the meniscus must be, it must be like this and it must be like this, is it? So some radius of curvature R2, right? So the pressure on this side, concave side, must be higher. So if this is the condition, I will write the lower meniscus will be concave upward, and the radius I can get, actually here I got P1, this pressure is P1, and here it's P2, that is equal to P naught. So P1 minus P2, is it, that is equal to how much? P naught minus 2T divided by R1 plus rho GH minus P naught. So this comes out to be rho g h minus 2t by r1, and this should be equal to what? 2t divided by r2, right? So this way we can get the radius curvature r2 comes out to be, this implies r2 is coming out to be 2t divided by rho g h minus 2t divided by r1. And if this is the condition satisfied, then the lower meniscus will be concave upward and the radius of curvature can be given by this way, is it? Similarly, here next condition will be if P1 is what? Equal to P2, right? That means pressure on both sides of lower meniscus is equal. Pressure on both sides of lower meniscus is equal so it will be flat, right? In that situation, the situation will be like this, upward concave, and lower will be like this, and this condition will be like P1 equal to P0 minus 2t by r1 plus rho g h, this is equal to P0, this, and that implies 2t by r1 is equal to rho g h. So if this is the condition, in that situation it will be flat r1, and this is height h, density of liquid is rho. And the next case is, we can write if pressure on lower side is higher, is it? I write P2 is greater than P1, that means pressure on lower side will be higher, so that means it must be in this orientation. Here it's P2, here it's P1, and this is P0 r1. So in this situation, the radius of curvature r2, is it? So here we can write the delta P, axis pressure will be P2 minus P1, that will be P0 minus 2t by r1 plus rho g h, and that will come out to be P0, this is 2t divided by r1 minus rho g h, that will be equal to 2t divided by r2. So we will get the axis like radius of curvature of the lower meniscus, and it will be concave downward, right? And lower meniscus will be concave downward. So in which case, what will be the meniscus, what will be the shape of lower meniscus, we can exactly comment depending on which is P1 is greater, P2 is greater, and so on. Remember what I mean here, P1 and P2 actually. In different books you might be given like these things in different way. The logic and ultimate result will be same, but the explanation or the terms may be different, so just take care of that. Here I am writing simply pressure at this point and pressure at lower, I mean top and bottom of lower meniscus. Based on that condition, if pressure on this side is higher, means it should be concave upward. If pressure equal, means it will be flat. Pressure on downside higher, means it should be concave downward, right? So this is about basically shape of lower meniscus, we can comment on that. Okay, so the next case is consider a liquid between two plates. So here we are having two plates, and let's say a liquid drop or water drop is placed between two plates. Then what will happen? It will spread between two plates, and depending on the property of liquid and is it angle of contact, surface tension, and all that, the orientation of liquid may spread in two ways basically. One, it may be spreaded in this way actually, or another case it may be spreaded like this, So this is the case of water between glass plates. So this is spreaded like concave outward, and this is the drop, so this is the liquid, and let's say the separation between them is d, and radius of curvature of this, I would say it's let's say r, and this angle of contact is theta, so this will be also theta, and this is d by 2. So we can write actually first relation, is it let radius of curvature for this is r, and for this surface I am taking, let's say, radius of curvature for this surface of curvature r, that is actually equal to infinity, and for this surface it's equal to small r, and I can write small r into cos theta is equal to d by 2. So small r is equal to d by 2 into cos theta. So first thing is it's concave outward, so means there will be excess pressure here and there will be small pressure or lesser pressure inside the drop. So as the liquid spread between the plates such that its surface is concave outward, so inside the drop pressure will be lesser. There will be excess pressure outside. So here I can write this P, let's say 1, and it's P naught. Then we can write basically here P naught minus P1, that will be given by what? T 1 by R1 plus 1 by R2, that is T surface tension, 1 by R plus 1 by R2 is infinity, so it's basically T by R. Substituting this, we are getting it's basically T into 2 cos theta divided by D. So that will be the basically excess pressure. So delta P can be written as 2T cos theta divided by D. Now here if theta is equal to 0, then we can write delta P will be equal to 2T divided by D. So we got the excess pressure basically, or lesser pressure. So what will happen actually in this situation? In this situation, here pressure is less and here pressure is more, P naught. So net these plates will be pressed downward, is it? So plates will be pressed closer, right? And to separate out, you need to apply additional force, is it? To separate them, force need to be applied. We can get that force actually if area of this is A, if liquid is spreaded in area A between plates, then force to separate the plates is given by delta P multiplied by area, that will be 2T cos theta into A divided by D, or if theta is 0, then you can write that is also equal to 2T into A divided by D. F to separate when theta equal to 0. So means like this is also like this type of problems are also in this situation. What will happen? There will be pressure inside axis, so it will like push the plates away. So you need to want to keep these plates at this separation, we need to press them from outside. we need to press them like this with this force, and here we need to separate them like this force. So this force will be equal to, similarly exactly in same manner we can calculate for this case also. So these are all different cases for related to surface tension, and this is all about theoretically for this chapter, surface tension. I hope you all understood things, and you try problems from your homework, whatever it's given, question bank, and practice it. And this is all about your surface tension. Thank you so much.